Hello students, welcome to Educate. In the last class, we have discussed about the properties of alcohols. In that class, we have also discussed some properties of phenols. In this class, we will discuss some chemical properties which is exclusively for phenols. Let's see, which is exclusively for phenols. Let's see here. First one is here, let's see, electrophilic substitution reaction. As phenols frequently will show electrophilic substitution reaction. Electrophilic aromatic substitution reaction, because when there will be electrophilic substitution reaction, that will be at the aromatic carbon only. As I taught you here, structure of HNO3 is like that. What happened? OH of this one, HNO3, that will combine with hydrogen of ortho position or of para position. That will form H2O, the electrophile NO2 plus. That will combine either at ortho position or at para position. So there will be, when the electrophile NO2 will bound to ortho position, that will be called orthonitrophenol. That is the common name. And IPAC name will be 2-nitrophenol. In the same way, when NO2 will be bonded to the para position, then IPAC name will be 4-nitrophenol and common name will be para-nitrophenol. Okay. One interesting fact about this orthonitrophenol and the para-nitrophenol is that the orthonitrophenol and the para-nitrophenol both can be separated through fractional distillation. There will be wide difference in the boiling point of orthonitrophenol and the para-nitrophenol. Why? Because in case of orthonitrophenol, there will be intramolecular hydrogen bonding. What is the meaning of intramolecular hydrogen bonding? That means hydrogen bonding will take place within the molecule. When hydrogen bonding will take place within the molecule, then that will be called intramolecular hydrogen bonding. And when the hydrogen bonding will take place between the two different molecules, between two molecules, when the hydrogen bonding will take place between two molecules, then that will be called intermolecular hydrogen bonding. While when the hydrogen bonding will take place in the same molecule, within the same molecule, then that will be called intramolecular hydrogen bonding. If you get confused, then just consider when you enter in the room, that means when you have just entering in the room, that means you are 1 feet outside your room and another feet inside the room. So 1 feet outside the room and 1 feet inside the room. That means you are connected that time between the environment of your room and that of the outside. So same here, intermolecular means the two different molecules will be bonded through hydrogen bonding. So in case of orthonitrophenol, how that is? Here, because OH bond, this OH and this NO2 are closer to each other. This OH and this NO2 is closer to each other. So hydrogen of this OH would bonded here to this oxygen. So that is called intramolecular hydrogen bonding. So if another molecule here, if there will be another NO2 molecule, then what will happen? Since the hydrogen has been already involved here in hydrogen bonding, so between these two molecules, that means this orthonitrophenol molecule and this orthonitrophenol molecule, the van der Waals force of attraction will operate, about which you already know that van der Waals force of attraction is the weakest force of attraction operating between the molecules. So here their boiling point will be very less. This one will be here, they will be bonded with each other through van der Waals bonding. and hence possesses less boiling point. But in case of para-nitrophenol, the OH group and the NO2 group are away from each other. So OH of this orthonitrophenol will be bonded to this nitro group through hydrogen bonding. The OH of this molecule is bonded to NO2 group through hydrogen bonding. So this hydrogen bonding, so it will be difficult to separate this molecule from this molecule. So therefore its boiling point will be high. So during the nitration of phenol, the orthonitrophenol and the para-nitrophenol so formed could be separated through fractional distillation, because the orthonitrophenol possesses less boiling point due to intramolecular hydrogen bonding, while the para-nitrophenol possesses high boiling point due to intermolecular hydrogen bonding. Okay. Next point here, when the phenol will be treated with conc HNO3. So what happened here? NO2, the number of NO2 electrophile will be very high. So the NO2 and electron, it is electrophile. NO2 plus is electrophile. So electron is at ortho position, at these two position and at this position. So the electrophile will bond at both the ortho position as well as at para position. So that's why 2,4,6 trinitrophenol will form, which is commonly called picric acid. Its acidic strength is comparable to the nitric acid and so on. So this is called picric acid. So when phenol will be treated with conc HNO3, there will be formation of 2,4,6 trinitrophenol. While when the phenol will react with dilute HNO3, there will be formation of the mixture of orthonitrophenol and the para-nitrophenol, and the mixture of orthonitrophenol and the para-nitrophenol could be separated through fractional distillation, as the orthonitrophenol possesses less boiling point and the para-nitrophenol possesses high boiling point. Okay. Now halogenation here. So when the phenol will be treated with halogen in presence of CH2 solvent, non-polar solvent, then what happen? Electrophile will be Br plus, that will bond either to the ortho position or at para position. Very easy. But when the phenol will react with bromine water, be in the mind here, when that has been reacted with in presence of CH2, then there will be formation of ortho-bromophenol or 2-bromophenol as well as the 4-bromophenol or the para-bromophenol. But when the phenol will react with bromine water, then the bromine will attach at both the ortho position as well as at para position. So this one is here. So there will be formation of 2,4,6 tribromophenol and it will be a white precipitate. So phenol here, that can be used to distinguish the phenol. Phenol is there or not, that you can also distinguish by bromine water test. When bromine water will react with phenol, there will be formation of 2,4,6 tribromophenol, which will be a white precipitate. PPT we also write by PPT. Precipitate we also write by PPT. Okay, about these questions we discuss later on. Firstly, it goes on the Kolbe's reaction. What happened in Kolbe's reaction? Here, firstly, the phenol reacts with NaOH. So there will be formation of sodium phenoxide, and then after this sodium phenoxide will react with CO2. How is this reaction taking place? Here, this one is CO2. Shape is linear. So of the ortho position, hydrogen will get bonded to this oxygen. So this double bond will dissociate to single bond. So the valency of this carbon atom will get destabilized. When hydrogen will bond to this oxygen, then the valency of oxygen will get fulfilled. But the valency of this carbon will get unsatisfied. That's why this carbon will get bonded to this carbon. So that's why here, and there is already C double bond O and C double bond O and OH. So that's why this COOH formed here. So that is called here COH here with at ortho position with respect to OH, then that is called salicylic acid. True hydroxybenzoic acid, obviously you could write the name, IPAC name very easily. Now in case of Riemann-Tiemann reaction, what happened here? This one I am telling you by writing the reaction. So what happened in Riemann-Tiemann reaction? During Riemann-Tiemann reaction, phenol is reacted with NaOH and chloroform CHCl3. So what happened about this reaction you are already aware. So hydrogen will combine with OH form H2O and this sodium will get bound. What happened here? In this case chloroform. So hydrogen of the ortho position that will combine with any carbon, any chlorine form HCl. Shape here is tetrahedral. So hydrogen will combine with any of the chlorine and form HCl. And CHCl2, valency of carbon will become destabilized. So this carbon will get bound to this carbon. So here will be so two chlorine will remain bonded and one hydrogen. That will, and then after pass water. So chlorine will bond to one of the hydrogen here. After that pass water here. So chlorine will bond to this hydrogen form HCl. This OH will get bond to this carbon. Same, another water molecule will be there. There will be not a single water molecule. There will be a number of water molecule. So this chlorine will combine to this hydrogen form HCl. So that means 2 OH group will bond to this carbon. So structure will be when the 2 OH group will be bonded to the same carbon, then that compound will be unstable. So hydrogen of one OH will combine with 2 other OH and form H2O. So same here, this hydrogen combine to this OH form H2O. So this oxygen will do the double bond formation to this carbon. Why the two, if 2 OH group combine to the carbon atom, same carbon, then unstable? Because this OH will be very close to each other. So that is the matter of chance that either this hydrogen will combine with this OH or this hydrogen will combine with this OH. So from where the hydrogen will release, that will depend on the matter of chance. So this oxygen will do double bond formation here. So what is the structure here? Remaining structure same as this. And here is C double bond O and here is hydrogen. Then after it will be treated with H plus, then sodium will release from there and there will be OH and here CHO. When there was COH group at ortho position with respect to OH, that was called salicylic acid. In the same way, when there will be CHO at the ortho position with respect to OH, that will be called salicylaldehyde. Okay, so this reaction is called Riemann-Tiemann reaction. In Riemann-Tiemann reaction, we prepare salicylaldehyde. Clear? In Colwich reaction, we prepare salicylic acid. Then after this reaction with zinc, this reaction very easy. Zinc will combine with oxygen here, form ZNO and hydrogen will get bonded. So there will be formation of benzene. When the phenol will be treated with a strong oxidizing agent, very strong oxidizing agent, then what happened? From here the hydrogen release, from here also hydrogen will release. And the oxygen provided from here, that will bond to the carbon of para position. So that is called benzoquinone. Keep in the mind, this is not an aromatic compound. This is aliphatic compound. This is benzoquinone. It is non-aromatic. This compound is non-aromatic. This is in text question. That was about the properties of phenols. Then after, let's see some questions about which I have told you to discuss later on. These questions you write by yourself. We have discussed already. Kolbe's reaction done. Let's discuss about this question. In this question is, you have to do mononitration of 3-methyl phenol. So firstly, draw the structure. 3-methyl phenol. So structure will be like that. Nitration means HNO3, you have to react with HNO3 in presence of H2SO4. So which electrophile form here? So NO2 plus. Now with respect to OH, the electrophile NO2 will bond to para position, and with respect to CH3, the OH will bond to para position or ortho position. So the OH could bond to this carbon also, and here ortho meta para to this carbon also. So here you write here or here. So compound will be here, in this case. So there will be 3 products. In this one case, this product will be the major product because NO2 group is at the para position with respect to OH. Among OH and CH3, OH donates their electron more frequently in the benzene. That's why we have to, about the position of this one, NO2, we will have to consider the position of NO2 with respect to OH, because OH donates the electron more frequently inside the benzene compared to that of methyl. Okay. Now second question here. So dinitration. So one NO2 you attach here and one NO2 here. No, not here. Why? Because with respect to with respect to OH, one NO2 here at para position, and the respect to methyl group, one OH, one NO2 will be at this position, at para position, ortho meta para. This is at the ortho position with respect to methyl and at para position with respect to OH. So that will be the major product. Third one is same here. Third one you can do very easily. Okay. So that was about the questions related to phenol. I'm watching any other. These questions firstly you solve by yourself. If in the next class also we will discuss these questions, you do in the homework. The questions about like Kolbe's reactions, Riemann-Tamer reactions, we have already discussed. So you could solve this question very easily. Why this one ortho and para nitrophenols are more acidic than phenols? Why? Electron withdrawing group. You can write that. Here, acid catalyzed dehydration, very easily you can do. So do this question by yourself. If you will feel any difficulty, then you may comment, and because already I have discussed the questions related to this one. So also I shall discuss about these questions only when anyone will request to solve this question, any one of this question. Okay, so that was about the essence of alcohol, phenols, and now there is some commercially important alcohols. About that we will discuss, and only ether, about ether we will have to discuss. So it's all for this class. In the next class we will discuss about the ethers and some commercially important alcohols. Okay, thank you, Team Educate.